As you know that coordination compounds is a very important class of compounds, and to understand coordination compounds or complexes completely, it is important to understand the bonding and structures of complexes. To understand that, today we are going to discuss valence bond theory for coordination compounds, applications of valence bond theory to complex ions, magnetic properties of coordination compounds, and limitations of valence bond theory. Before proceeding further, let us recall what we have discussed earlier. In last lecture, we discussed optical isomerism, optical isomers, optical activity, plane of symmetry method, and the mirror images method. Let us discuss valence bond theory now. In 1927, valence bond theory was formulated, and it argues that a chemical bond forms when two valence electrons in their respective atomic orbitals work or function to hold two nuclei together by virtue of effects of lowering system energies. Building on this theory, the chemist Linus Pauling published in 1931 one of the most important papers in the history of chemistry, Nature of the Chemical Bond. In this paper, elaborating on the works of Lewis and the valence bond theory of Hitler and London and his own earlier works, Pauling presented 6 rules for the shared electron bond, the first 3 of which were already generally known. The electron pair bond forms through the interaction of an unpaired electron on each of the 2 atoms. The spins of the electrons have to be opposed. Once paired, the 2 electrons cannot take part in additional bonds. His last 3 rules were new, and these were: the electron exchange terms for the bond involves only one wave function from each atom. The available electrons in the lowest energy level form the strongest bonds. Of the 2 orbitals in an atom, the one that can overlap the most with an orbital from another atom will form the strongest bond, and this bond will tend to lie in the direction of the concentrated orbital. A complex is formed when electron pairs from ligands are donated to a metal ion. This does not explain how the metal ion can accept electron pairs, nor does it explain the paramagnetism often observed in complexes. Valence bond theory provided the first detailed explanation of the electronic structure of complexes. This explanation is essentially an extension of the view of covalent bonding. According to this view, a covalent bond is formed by the overlap of 2 orbitals, one from each bonding atom. In the usual covalent bond formation, each orbital originally holds 1 electron, and after the orbitals overlap, a bond is formed that holds 2 electrons. In the formation of coordinate covalent bond, a complex, however, a ligand orbital containing 2 electrons overlaps an unoccupied orbital of the metal atom. Here you can see, in the usual case, each overlapping orbital contains 1 electron, and this is conventional covalent bond. But when a coordinate covalent bond forms, one orbital containing a lone pair of electron pair overlaps with empty orbital, and this is a coordinate covalent bond formation. Now we will discuss the salient features of theory. These are: the central metal loses a required number of electrons to form the ion. The number of electrons lost is the valency of the resulting cation. In some cases, the metal atom does not lose electrons. The central metal ion or atom, as the case may be, makes available a number of empty s, p and d atomic orbitals equal to its coordination number. These vacant orbitals hybridize together to form hybrid orbitals, which are same in the number as the atomic orbitals hybridizing together. they are vacant and equivalent in energy and have same definite geometry. Now, some of common hybridized orbitals met in the coordination compounds are listed here. For coordination number 2, hybridization is sp and geometry is linear. For 3 coordination number, sp2 hybridization takes place with trigonal planar geometry. For 4 coordination number, if hybridization is sp3, geometry is tetrahedral, but if hybridization is dsp2, the geometry is square planar. For 5 coordination number, 2 types of hybridization will take place, dsp3 and sp3d. With dsp3 hybridization, trigonal bipyramidal geometry will be formed, and with sp3d hybridization, square pyramidal geometry will be formed. Similarly, for coordination number 6, there will be 2 types of hybridizations, d2 sp3 and sp3 d2. With d2 sp3, geometry will be inner orbital octahedral, and with sp3 d2, geometry will be outer orbital octahedral. The non-bonding electrons on the metal occupy the inner orbitals. These are grouped in accordance with Hund's rule. However, under the influence of some strong ligands, there may be some rearrangement of electrons in the atomic orbitals. This rearrangement is often against Hund's rule. There are 2 types of ligands, namely strong field ligands and weak field ligands. A strong field ligand is capable of forcing the electrons of the metal atom to pair up if it is required. Pairing is done only to the extent which is required to cause the hybridization possible for that coordination number. A weak field ligand is incapable of making the electrons of the metal atom or ion to pair up. Some examples of strong field ligands are Cn minus, CO, En. Here CO is carbonyl and En is ethylene diamine. Some examples of weak field ligands are I minus, Br minus, Cl minus, F minus, NO3 minus, OH minus, C2O4 2 minus. The ligands have at least one sigma orbital containing a lone pair of electrons. Vacant hybrid orbitals of the metal atom or ion overlap with the sigma orbitals containing lone pair of electrons of the ligands to form ligand to metal sigma bond. This bond is called coordinate bond. It is a special type of covalent bond and possesses a considerable amount of polarity. It is possible to predict the magnetic properties of the complex if the geometry of the complex ion is known. If the complex contains unpaired electrons, it is paramagnetic, and if it does not contain any unpaired electron, that is, all the electrons are paired, the complex is diamagnetic in nature. Complexes having unpaired electrons are colored. Now we will discuss the applications of valence bond theory to complex ions. Valence bond theory treats ligand to metal bonds as coordinate covalent bonds formed when a filled orbital of a donor atom overlaps with an empty hybrid orbital of the central metal atom. The molecular geometry is predicted using VSEPR theory. The theory proposes that the number of metal ion hybrid orbitals occupied by donor atom lone pairs determines the geometry of the complexes. Lone pairs of electrons on metal ion or atom are ignored. Since lone pairs are in the inner shell, they are believed to have little effect or no effect on molecular geometry. Let us discuss two coordinated compounds now. Two coordinated compounds have sp hybridization and they are linear in geometry. Here you can see AgNH3 2 plus. As silver is in +1 oxidation state, hence its electronic configuration will come out to be 5s0 4d10. There will be no electron in 5s. Here is the electronic configuration of silver plus. Now, for coordination number 2, we require 2 orbitals. Therefore, 1s and 1p orbital will hybridize to provide 2 sp hybridized orbitals, and this complex will form sp hybridization and linear geometry. Here is another example with sp hybridization CuCN2 minus. Here also copper has electronic configuration 4s1 3d10, and as copper is in +1 oxidation state, it will have a configuration 4s0 3d10, and as in previous example, here also sp hybridization is required to fulfill the coordination number 2. Now we are going to discuss 4 coordinated compounds. In tetrahedral complexes, 1s and 3p orbitals are hybridized to form 4 equivalent orbitals oriented tetrahedrally. Here you can see zinc has the electronic configuration 4s2 3d10, and in +2 oxidation state, it will not contain any electron in 4s orbital. Here is the electronic configuration of zinc +2 ion. For tetrahedral geometry, or we can say for coordination number 4, we require 4 empty orbitals. Therefore, 1s and 3p orbitals will hybridize to give 4 sp3 hybridized orbitals, and 4 ligands will donate their lone pair of electrons in these 4 sp3 hybridized orbitals, and this complex will attain a tetrahedral geometry. Another example for tetrahedral geometry is CdNH3 4 plus 2. In this case also, in cadmium 2 plus, 5s orbitals will not contain any electrons, and 1s and 3p orbitals will provide 4 sp3 hybridized orbitals, and tetrahedral geometry will be attained. Let us discuss the 2 types of geometries in 4 coordinated complexes of nickel 2 plus. Here is the example NiCl4 2 minus. As nickel in +2 oxidation state, hence its electronic configuration is 4s0 3d8. Here is the electronic configuration of nickel 2 plus. As it is a 4 coordinated complex, hence 4 empty orbitals are required. Therefore, 1s and 3p orbitals will hybridize to give sp3 hybridization and a tetrahedral geometry. Each chloride ion donates a pair of electrons. The compound is paramagnetic since it contains 2 unpaired electrons. Similarly, NiCO4 has tetrahedral geometry, but it is diamagnetic since nickel is in 0 oxidation state and contains no unpaired electrons. In previous examples of tetrahedral geometries, sp3 hybridized complexes, the ligands donates electrons to the vacant sp3 hybrid orbitals. This is true when weak ligands are present. However, with strong ligands such as Cn-, 2 unpaired electrons in half-filled 3d orbitals are forced to pair up with each other, creating an empty 3d orbital. This gives rise to d-sp2 hybridization and square planar geometry. When very strong ligands are present, 4 coordinated d8 metal ions usually form square planar complexes rather than tetrahedral. An example is NiCN4 2 minus. Nickel in +2 oxidation state will have the electronic configuration 4s0 3d8. Here is the electronic configuration of nickel 2 plus, but in the presence of a strong feed ligand Cn-, these 2 electrons are forced to pair up. Here you can see the pairing of these two electrons. Now, the 4 orbitals required to fulfill the coordination number 4 are 1d, 1s and 2p, and we will have the hybridization dsp2 and a square planar geometry. Each of the hybridized orbitals receives a pair of electrons from a cyanide ion. The compound is diamagnetic as evident from the absence of unpaired electrons. Let us discuss 6 coordinated compounds which have an octahedral geometry. The metal ions in which 2d orbitals are vacant will form inner shell hybridized d2sp3 octahedral complexes. Metal ions in which 2d orbitals are not vacant will form either outer shell sp3 d2 hybridized octahedral complexes with weak ligands or inner shell d2 sp3 hybridized octahedral complexes with strong ligands. If half-filled d orbitals are present, a low spin state is forced. Here is the example of FeCN6 3-. As you know that Cn is a strong field ligand. So, here is the Fe3+ configuration, and because of the presence of strong ligands, these unpaired electrons are forced to pair up, and the 6 empty orbitals which we require to fulfill the coordination number 6 are d2 s p3, and the complex will have a geometry inner orbital octahedral. You can note that Cn- is a strong field ligand forcing inner 3d electrons into a lower spin state and hybridizing inner 3 orbitals, that is d2 sp3. Now we will discuss another example of 6 coordinated complex with a weak field ligand. FeH2O6 3+. Here also iron is in +3 oxidation state, and here is the configuration of Fe3+. As H2O is a weak field ligand, hence there will be no pairing of the electrons in 3d orbital. Therefore, the 6 orbitals which are required will be 1s, 3p and 2d. The hybridization will be sp3d2, and the complex will have the geometry outer orbital octahedral. It is usually possible to predict the geometry of a complex from the knowledge of its magnetic behavior on the basis of the valence bond theory. In the diamagnetic octahedral complex CONH3 3+, the cobalt ion is in +3 oxidation state and has the electronic configuration 3d6. The orbital diagram of this complex can be seen here. The electronic configuration of cobalt 3+ is 3d6, which is shown here. As it is said that this complex is diamagnetic, therefore, it is clear that these electrons are paired. Now, the 6 orbitals which are required are d2 sp3. Therefore, this complex will attain inner orbital octahedral geometry and the molecule is diamagnetic. The paramagnetic octahedral complex COF6 3- uses outer orbitals, that is 4d orbitals in hybridization sp3d2. It is thus called outer orbital or high spin or spin free complex. Thus, for this complex, here is the electronic configuration of cobalt 3+, which is again 3d6. As the molecule is paramagnetic, therefore, these electrons are not paired. Now, the hybridization which is attained is sp3d2 and the geometry is outer orbital octahedral. Now, we will discuss the magnetic properties of coordination compounds. You know that A substance which do not contain any unpaired electron is not attracted by a magnet. It is said to be diamagnetic. On the other hand, a substance which contains one or more unpaired electrons in the d orbitals is attracted by a magnet and it is said to be paramagnetic. Paramagnetism can be calculated by the expression mu equal to under root n into n plus 2, where mu is the magnetic moment and n is the number of unpaired electrons. Therefore, if n is equal to 1, magnetic moment will be equal to under root 3, which is equal to 1.73 Bohr's magneton. If number of unpaired electrons is equal to 3, magnetic moment will be equal to under root 3 into 3 plus 2, which is equal to under root 15 equal to 3.87 Bohr's magneton, and so on. On the basis of the value of magnetic moment, we can predict the number of unpaired electrons present in the complex. If we know the number of unpaired electrons in the metal complex, then it is possible to predict the geometry of the complex species. The magnetic moment of coordination compounds can be measured by the magnetic susceptibility experiments. The results can be used to obtain information about the structures adopted by metal complexes. The number of unpaired electrons and the geometries of the complex ions having central metal ion with configurations D1 to D9 are related to each other and are shown here. For D1, D2 and D3 configurations, there is no difference in the number of unpaired electrons for the 3 electronic configurations for tetrahedral, square planar, inner orbital and outer orbital octahedral geometries. But for D4 geometry, 4 unpaired electrons are there for tetrahedral, 4 for square planar, 2 for inner orbital octahedral and 4 for outer orbital octahedral complexes. Similarly, for D5, 5 unpaired electrons are for tetrahedral geometry, 3 for square planar, 1 for inner orbital and 5 for outer orbital octahedral complexes. For D6, 4 for tetrahedral, 2 for square planar, none for inner orbital and 4 for outer orbital octahedral complexes. For D7, 3 for tetrahedral, 1 for square planar, 1 for inner orbital octahedral which is shifted to higher orbitals, and 3 unpaired electrons are there for outer orbital octahedral complexes. For D8 configuration, 2 unpaired electrons are for tetrahedral, none for square planar, none for inner orbitals, that is the 2 electrons are shifted to higher orbitals and 2 unpaired electrons are there for outer orbital octahedral. For electronic configuration D9, 1 unpaired electron is for tetrahedral, 1 which is shifted to higher orbitals is for square planar, 1 unpaired for inner orbital octahedral where 3 electrons are shifted to higher orbitals and 1 unpaired electron is for outer orbital octahedral complexes. Valence bond theory is very important theory to understand the structures and geometry of complexes. But this theory also has some limitations. Let us discuss these limitations now. The origin of their absorption spectra could not be explained. It does not explain the color exhibited by coordination compounds. It does not give a quantitative interpretation of the thermodynamic or kinetic stabilities of coordination compounds. It does not explain as to why should certain ligands form high spin while others low spin complexes. The changes in energies of the metal orbitals on formation of complex are difficult to calculate mathematically. It does not make exact predictions regarding the tetrahedral and square planar structures of 4 coordinate complexes. It does not distinguish between weak and strong field ligands. Sometimes the same metal ion assumes different geometry when formation of complex ion takes place. The theory is unable to explain why at one time the electrons are rearranged against the Hund's rule of maximum multiplicity, while at other times the electronic configuration is not disturbed. It does not explain the temperature dependence of magnetic properties. These were some limitations of valence bond theory. Now let us revise what we have discussed today. Today we talked about valence bond theory for coordination compounds, application of valence bond theory to complex ions, magnetic properties of coordination compounds, and limitations of valence bond theory. With this lecture, we come to the end of this unit, coordination compounds. In this unit, we learnt about nomenclature of coordination compounds, ligands, types of ligands, isomerism in coordination compounds, bonding, that is valence bond theory, and geometries of complexes.